Hello and good morning or afternoon, depending on where you are located in the world. And welcome to the third AskTOM office hours session for graph technologies. Today, our focus topic is Gain Insights with Graph Analytics. My name is Jean Im. I'm a product manager on the Oracle Spatial and Graph product team. And today with me are my good colleagues and graph experts, Albert Godfriend. He's our Spatial and Graph Solutions Architect Extraordinaire, dialed in today from beautiful Nice, France. And across Europe and the Middle East, Albert works extensively with customers and partners, as well as delivering presentations and workshops on spatial and graph technologies. And with me in cloudy California today, Northern California, is Zi Wu, our amazing architect for our graph technologies. He wears many hats, driving development of our graph technologies since their inception, and as well finding the time to work extensively with several customers and partners. A few housekeeping notes to folks before we start. All of your lines are muted, so please use the chat to ask any questions. And again, we do encourage your questions throughout. The goal of office hours is to help you with your development ideas, so don't be shy. We'll be monitoring that throughout the session, and we'll try our best to address all of your questions. Remember that we can't discuss any SRs or bug reports or licensing issues on the call. If you do post any code into chat, just remember that everybody can see it unless you direct the chat post specifically to the hosts. Great. So Albert, next slide, please.
There you go.
Thank you. Today, in our third AskTOM property graph session, we'll be covering, as I mentioned, gaining insights with graph analytics. To bring you up to speed, we've had two previous sessions. The first one in February covered an introduction to property graphs and use cases. And in March, we covered how to model graphs from your relational data. The website above is the property graph AskTOM landing pad. If you missed any of those prior sessions or want to review the recording from today later on, refer to that website. It also has resources such as a registration page, a feedback and topic page, and an area to view and sign up for future dates of sessions. So make sure to bookmark that. Today, we'll look at graph analytics and see the power of graphs to understand relationships in your big data and to answer questions and see patterns in that data where relational technologies can't. Next slide, please. So the story so far, I'll start off with a brief 10,000-foot intro that recaps our last sessions before we dive in. So just to review, Oracle has two software products that support graphs. We have Big Data Spatial and Graph to manage graphs in big data environments like Hadoop, NoSQL, and HBase. Oracle and Spatial and Graph is our product for relational databases. And both are available on premises or in the cloud. In AskTOM, we'll focus mostly on the database graph technologies, but bear in mind that many of these technologies are similar, if not identical, on the big data platforms, and this information can be applied there. Next slide, please. So we'll just review quickly the architecture as well. From the bottom up, we provide highly scalable and secure storage. And again, you have a choice to use Oracle Relational Database 12.2 or 18.1, or big data stores like Apache HBase or NoSQL database. In the database, this allows us to leverage technologies like database parallelism for very high performance. In the middle, we have a common data access layer, or DAL. This Java layer allows application developers to query, fetch, and filter graph data from the database through Java, JDBC, or SQL. We also expose Blueprint's APIs and provide integration with text engines like Lucene and Solar Cloud. And on top, to analyze the data, here's where the power and the magic come in. We have an in-memory graph analytics engine called PGX. PGX can read graph data from storage very efficiently through the DAL layer into an in-memory data structure. We provide 50 analytical functions out of the box, plus PGQL query, so that you can define and run queries across your graph data set without being a graph expert having to build your own algorithms. These are pre-built algorithms. On the top left, to visualize data, we provide integration with an open source visualization tool called Cytoscape. And on the side, you see we provide several different interfaces for developers or users to access this rich set of functions. Java, Groovy, Python wrappers, REST services, web services APIs, and notebook interfaces, some of which you'll see later today. And we also support various property graph formats, flat files, and integration with Spark, useful for machine learning environments. Next slide. What is a graph? To review, it's a data model that represents entities as vertices and relationships as edges with optional attributes. So this is a very flexible data model. No predefined schemas involved. It can be extensible. And the power here is it enables new kinds of analytics that are not possible or very onerous to perform using relational technologies. Next slide. What kinds of insights can graph analysis provide? When we apply graph analysis to social networks like Twitter or Facebook data, or data in IoT networks, sensor data, or even financial transaction data, graph analytics answers a wide range of questions about relationships, including who are the most influential individuals in a network? How can we identify patterns of fraudulent behavior, for example, among financial transactions? Or what products can we recommend based on what similar customers are buying? And industries like banking, finance, public sector and intelligence, retail and manufacturing are rapidly adopting these technologies. So today, Albert will show how to perform graph analytics with our technologies, with our APIs, and then Z will share with you what you can do with them. He'll dig deeper into some of these use cases and how analytics can help you answer those questions. So Albert, handing over to you.
Thank you, Jean. Can you hear me? Is that everything clear?
Yep.
Okay, good.
Yep.
I was never sure. Right. So, like Jean just said, I'm going to talk about the APIs from a perspective of how they are. How do you use them? What code you write? What tools you use to access them? And then G will give us some practical examples of how these APIs can be put to use. First of all, again, the architecture. We are going to focus on this top box, graph analytics, which you also tend to call PGX. The underlying layers like DAL and then the storage at the bottom. Well, that's where we store the graphs. Everything we show you today works irrespectively of the storage media, whether it's RDBMS, HBase, or NoSQL. And we achieve this isolation thanks to the DAL layer. So DAL layer is the one that is used to create the graphs, to populate the graphs, to manage the graph store. And that's essentially what we covered so far in the previous session. So today we'll stick on, we'll cover on PGX. Well, the API, the core API is Java. Here you see a screenshot of the Java doc for the PGX API. There's also a DAL API. That API is the same for all three storage models that we support. Even though here it says Oracle Big Data Spatial and Graph, that API is exactly the same for database spatial and graph. So there's no difference on that level. How do you use the API? I'm going to concentrate on the Groovy shell access and notebooks access. G will actually show you also how the APIs can be invoked through Python bindings. We also have R bindings and also JavaScript bindings. But here we concentrate on the Java Groovy shell API. Now, Groovy, if anybody is not familiar with it, is essentially a multilingual interface that has one really nice feature, and that is that it provides shell access. So it essentially provides something like interpreting Java code. And this is really nice for testing, also nice for their scientists to get familiar with the data, with the APIs, and use them. So that just shows how we run the PGX API. It's the same thing that actually shows it from the Oracle Big Data Spatial Graph as well as the Oracle Database Spatial Graph. It's just a different ways to invoke the shell script, but everything else is just the same from that point on. So in order to run the analysis function, there's also something important to understand. We need to go through some preparation steps, like get an in-memory analyst, create a session, get an analyst, and then importantly, read the graph in memory. All the graph analytics happen in memory. So there's that first stage to read graph in memory. Now, in future session, we will talk about how the graph analytics can be deployed, how this architecture that we saw with PGX and DAL can physically be deployed as separate servers, and we will learn that it's possible to, for one session, to load the graph and then share that graph with other users, or for the graph server to just automatically load one or more graphs and have these accessible. Here we're looking more in this, what we're looking at here is like the single user case where I create a session and I read the graph in memory. And then once this is done, I can start using the analyst object I created and do analytics like count triangles, page ranking, connect components, or running PGQL. Not everybody likes command line. I'm okay with command line, but there are better ways of doing that. And a very common way nowadays for storing command line code and sharing the code and reusing, modifying that code is notebooks. One of the notebooks I'm going to talk about here is called Zeppelin. Zeppelin works by letting you create these notebooks, and then by filling these notebooks with things called paragraphs. Specifically for Zeppelin, we provide a plugin, an interpreter called interpreter that we call PGX. So PGX is something you need to add to your Zeppelin installation if you're running it. It comes with the property graph installation kit. There's some configuration needed, and what I highlight here is the main configuration parameter, which is a pointer to the PGX service, the PGX server. So that assumes that outside of Zeppelin, you actually started the PGX server, and then multiple people can then connect and share that common PGX server. Right? So that's how a Zeppelin notebook looks like. And maybe rather than showing you screenshots here, I will try and be brave and actually run a live demo. So I hope this works here. Actually, I'm going to use another window. I have no, wait a second. I thought I had it up anyway. That's okay. I'll just start it from here. So Zeppelin. This starts my, can everybody see this? That screen? Like, Jean, can you see the screen here?
Yes, it looks good. Thanks.
Okay, so that's Zeppelin running. I have created a few notes for the notebooks. One of them is this, Graph Analytics for today's specific talk. And so notebooks work by you defining things called paragraphs. Here you see a number of paragraphs. Paragraphs are interpreted by interpreters. And you see two kinds of paragraphs here. The first one, load graph, is actually a markdown interpreter, which essentially lets you add text to your graph, to your notebook. So not just have executable, but also have explanation documents and documentation about what this is doing. So here I just use this to use it to add titles to. I'm sorry, I wanted to run this. So just add titles to my notebook. Then underneath we see our first executable paragraph. You see %PGX, that identifies the interpreter we're using, so the PGX interpreter, and then the rest here is essentially Groovy code. So the steps we are going through here are, first of all, to set up a configuration to the graph we are loading. So you see something like a graph config builder. This is for NoSQL. So we see for property graph NoSQL. Big Data Lite 5000 is the pointer to my my NoSQL my NoSQL server. KV Store is the name of my NoSQL database, and connections here is the name of the graph I have in there, right? So this is for NoSQL. If you wanted to use like the Oracle database, it would just be different. It would be more like a JDBC connection with the usual server name, port 1521, database service name, username, and password. The next steps here, add vertex property and add edge property. This is to specify which of the properties of my graph I want to load in memory. Graphs can be very large. Vertices and edges can have many properties. And that means and since I load them in memory, I need a lot of memory to host these graphs. Now, I may not want to load my entire graph in memory. First of all, I may want to select which vertices I want to load, because I just maybe want to deal with certain kinds of vertices. Maybe I want to analyze, let's say, financial fund transfers, but only for the last year. However, my graph has all the maybe 10 years of history of fund transfer. I don't want to load the whole thing, so I can select that now. That is done by applying filters. I'm not going to talk about that here too much, but also may not need to load all the properties. Properties take space, they take room in memory. So I just need to specify which properties I really want to load so that I can use them in my analytics. In this case, I specify name, role, occupation, country, religion, because I use them in analytics. I can also specify which properties I want to load for the edges, specify the label, the build, and so I'm going to execute this. And executing paragraphs is this. I just click the arrow button. The response here is a JSON configuration of my graph. And then the next step is to read the graph in memory. Okay, that's done. Now, this is obviously a very tiny graph. We're looking at like a very simple, like I think less than 100 nodes and 100 vertices and 164 edges, so it's very small. Obviously, a bigger graph will take longer to load. Now my graph is loaded. I can now look at, well, how big is it? How many vertices? How many edges? I can also find out how my vertices are organized, which properties do I have. And once I have done that, I can now start running analytics. Here is an example of running a PageRank analytics. So you can see it is like what I showed earlier. It's using the analyst object. I did not create that analyst object. That was created automatically by the Groovy shell, was invoked by the interpreter, by notebook, calling the PageRank method, telling it which graph to use. It's PG, that's my graph name. It's called PG. And then other parameters. And then I'm getting the top 10 values. Right, so now here we start seeing some interesting benefits of using notebooks as well, and that is that the output can be formatted differently in different ways. That is the default formatting. It's a table. It's an array of values. So this actually returns key value pairs. One is the vertex ID, and that is the page rank we computed. Now I can see this easily as a graph, like maybe as a bar chart, as a var chart like this, or maybe as other like line charts and other ways, other graphical ways. Similarly, betweenness centrality will compute the betweenness centrality of my graph, and again they get top k values. We return the top 10 values, so ordered by the value of centrality, and I can see this. That is, of course, there are many more of these functions methods, and we'll talk a bit more about them. And then G is going to show you some practical uses. Where would you actually use PageRank? What does it do for you? Where, in which circumstance would you use betweenness centrality? What it would do for you? Now here at this level, there's a little problem with the result though, because what I see here is the vertex ID and the value. But what I would like to know is what vertex is it? Not the internal ID, but like in this case, the graph is about people. It's called connections. Which people are these, right? And there's an easy way for doing that. I can, of course, write code, like a loop that will actually extract the values from here and then individually selects the properties I want to display. But I can do it in an easier way. And that easier way is now going to go through PGQL. Okay, PGQL is complementary to the analytics. So on the one side, we provide pre-computed and predefined analytics functions like PageRank, And then on the other side, you also provide you with a language that you can use to explore graphs. This will be used for things like detecting loops in a fraud case, and G will show you examples of that, how that is done. Here we are going to use it for something simpler, which is to actually expand on the result that were being captured by the page rank. The main effect of the page rank argument was to expand the vertices with additional properties that have been computed on the fly. And for page rank, that property is called approx page rank. And I think we should be able to see this. If I rerun this here, we should see that we now have two additional properties. There's one called approx page rank that was filled by the PageRank function, PageRank method, and betweenness that was filled by computing the betweenness centrality. And now I can use this here. I can just write this simple PGQL, which is which does something which fetch everything from my current graph. There is no from clause here because there's implicitly just one graph. So it is from the current graph, where X is like a dummy where clause. It's think of it as a select star from table where X, and X is a placeholder because it's in round brackets of vertices. I'm fetching x.id. ID is a built-in method of the vertex that gives me the ID, so the unique number of that particular vertex. Name fetches name property. Approx PageRank fetches the PageRank property. And I'm going to order this by PageRank, descending limit 10. So give me that will give me the top 10 PageRank, the top 10 most important, at least persons from the PageRank point of view. Okay, and here they are. The ID, name, and PageRank. And now I can also do that again in as a graph. And now I see something which is much more useful. I see who has the highest PageRank, who has the nearest PageRank, etc. And again, I can do that maybe as a pie chart, and that will show it differently. Similarly, fetching the betweenness results is going to be done the same way. So I'm going to execute the paragraph, run similarly x name, x betweenness, ordered by betweenness descending, limit 10, and I get a tabular result. And again, that can be shown in a different way that is maybe more interesting. Other things I can do here, plenty of things we can do here. I just want to highlight a couple more queries. This one here is does the following. It will this actually will tell me how many different relationships I have in my graph, which I do by counting how many edges I have and group by label. Okay, group by label, order by count, descending. I imagine that most of you, if not all of you, are very familiar with SQL, and you will see this is very much like SQL. Select E, label, count, group by, order by, descending is much like SQL. What makes this different from SQL is this expression here, where n square bracket E greater than, etc. N, so the N and M are vertex placeholders. So because they look a bit like round circles as they are usually used to representing graph. And this thing in the middle is actually looks like an arrow if you think about it. There's a square marker, and the E is actually the label that indicates the edge, so a placeholder for edge. And so what we do here is essentially fetch all the vertices and all the edges between any two vertices, and then get the label of each of these edges and compute a count, how many they are, group by, and get a result. So the result will be like this. There are essentially 1, 2, 3, 4 different kinds of labels in our graph: collaborates, feuds, admires, and leads. And here we see them by quantity, and of course that lends itself very nicely into being rendered as a pie chart. Similarly here, this will again analyze, fetch everything from my graph, except I'm restricting the query to those edges who are covered by or represent the collaborates relationship. So the collaborates edges where the label is actually collaborates. And now I'm going to get the name and the count of people who are connected, so to anyone else in a collaborate relationship, group by n, so group by vertex, and again order by count descending limit to 10, the top 10. So this tells me now which of my of them on graph are the most collaborative, the one who have the largest number of collaborators. And again, we can see that as a pie chart or as a graph like this, as a pie chart or histogram. Right. So you can see that notebooks make things much easier for you to try things out rather than going through fully command lines. Like this would be the same. Let me see. I'm going to show you an example of how this would be done from the command line. Like here is an example of running PGQL from the Groovy shell command line. You can do exactly the same thing. You get the same results. There are commands to beautify the results, but of course here, being a purely command line interface, there are no graphics available. So no nice pie chart, no nice histograms. So there are many of these analytics. There's a large number. I think something like over 40 different kinds of analytics that are built in. To learn more about these things, what they are doing and where they are used, at the end we will show you a pointer to where you can get that kind of information. But they do things like PageRank is to find influencers in a social network. Who are the important vertices, maybe in a graph that represents dependencies in your IT infrastructure, sparsification, trimming down the graph, clustering, finding communities. So again, social graph, people who have similar interests that are basic, that can be used for market segmentation, recommendation, breadth first searches, shortest path, discover how things are connected to each other, how many steps are there between multiple people, transportation routing as well, metrics factorial recommendation, centrality for, again, critical people, finding that very critical device or router that everybody depends on, SALSA, graph filtering, etc. Also text searches, although text searches will be done more in a DAL environment. There's also spatial searches and filtering. Right. With that, I'm going to hand over to Guy, who's going to show us a few use cases where these things are put to practice.
Thank you, Albert. Can you hear me all right?
Yes, I can.
Okay, great. Could you stop sharing so that I can share?
Yes, true. I need to do that. There you go.
Okay, thank you. So the slides is visible now, right?
Yes.
Yeah.
Fabulous. So now let's take a look at a few use cases and how graph analytics, right, can help address the core requirements of these use cases. The first one is to build a recommender system with graph database technologies. Well, I guess most of you are familiar with recommender system. It's actually really big topic. There's a lot of details, but in the interest of time, I'm going to cover just the core part of the algorithm. Very basically, right, a recommender system is to recommend items, right, to users. Like the graph you're looking at on the left-hand side, you see several users. On the right-hand side, you see several products or items or services. The idea is that, given your past history of clicking or purchasing or saying, hey, this is great, this is not good, right? Given all those, right? How the system can recommend new products, new items, new services to different individuals. With Oracle property graph database technologies, there's a few ways you can tackle recommender system. You can use content-based filtering. So essentially, this one is using text matching. Right? If you have an item with, say, wireless speaker, if you have user, with profile showing interest in certain speakers or wireless technologies, and then this can be potentially a match. Right? For this, we use Solar Cloud. We index the user's profile, or we also index items description, all those text fields, and then we rely on the relevancy ranking and essentially cosine similarity, right, to find items that match a user's profile or interest. The second one is the collaborative filtering. Okay, the idea is very simple. People liked similar items in the past, right? We tend to like similar items in the future. So if you look at this matrix in the middle of the screen, there's users, right? Here, there's a list of items as the column. Okay. Well, as you can imagine, if you have a million user and million items, this matrix is going to be huge. And we all know, as individual, you cannot, rate every single items out there. Right? It's just impossible. So you will have a very limited number of, say, hey, I like this one 5-star. I really hate that one, 1 star. Right? So this matrix is going to be a sparse matrix. And in some of the cells, in a very small number of the cells, you will see ratings, right? 5-star, 4-star, 1-star, etc. And the idea of collaborative filtering is trying to, use some algorithms like a matrix factorization to fill in the blanks, so that although a user hasn't really purchased or rated an item, we can predict the kind of rating the user is going to have on a particular item. So essentially, the algorithm will fill out the blanks, okay, in this very sparse matrix. The third algorithm we offer out of the box is personalized PageRank. Many of you are familiar with PageRank, right? It's pioneered by Google, Baidu, those search engines. It's a way to, find the influencers. Essentially, right? You have a network of web pages, and this algorithm can compute PageRank values in an iterative fashion, and then come up with values so that you know which page is more important than other pages. Now, translating to this recommender system, if we arrange the graph in a bipartite graph, right? The left-hand side uses right-hand side items, right? So we can use random walk, okay? For example, start from A, then jump to an item, follow a reverse edge to another user, and the difference between personalized PageRank and PageRank is, with PageRank, right, periodically with certain probability, you jump to a random vertex in the graph. With personalized PageRank, periodically with certain probability, you jump back to one of the starting points. So by doing this, you can easily find vertices that are similar to your starting point. Okay, in this case, if you start from a particular individual, then you can easily find similar users, okay, as your starting point. You can also find similar items. And the similarity is really the key to recommender system. So now let's look at the PPR, personalized PageRank. Just a very simple example, right? We have John, Mary, Jill, and Todd on the left-hand side. Those are users. We have iPhone 5, Kindle, etc. Right? 5 different items on the right-hand side. So if we start with John, I just want to show this to you, right? If we do random walk, follow one of the outgoing edges, right, to iPhone 5, and then follow the reverse edge back to Mary. So this kind of a random walk, right? And periodically we jump back to John, assuming John is the starting point. It's quite easy to see because Mary, right, has clicked these 2 items before, and John has clicked these 2 items before. So it's really easy to reach Mary, right? John to iPhone 5, back to Mary, or John to Kindle Fire, back to Mary. it's a lot harder for John to reach Todd because they don't share many of the items. Okay, so therefore, if you perform personalized PageRank, you will see John and Mary will have a very high PPR value. Okay, if you start from John, and Todd will have lower PPR value. So this is essentially the key idea behind PPR. And I also have a blog here, so you can take a look when you have some time, which explains in an intuitive fashion PPR. Well, to run personalized PageRank is really straightforward, as Albert has shown in the very nice notebook. Right? You have a paragraph, but then the key thing is really just one simple API call, right, to compute a particular analytics. Right? In this case, we run PPR. The API is shown here in blue font, personalized PageRank. You give a vertex, set, right? This is your starting point or starting points, depending on the size of the set. And then you can iterate through the result set, and you can rank them. So this is a PPR value here, as as you can see, John has the highest PPR, and followed by some other vertices. So PPR can not only find similar users, but also similar items. So you can recommend new items based on PPR. You can also recommend, hey, this user has similar taste as you. Okay, so both are very interesting in practice. Let me take a look at the time. Another very interesting analytics to perform recommendations is use collaborative filtering, or CF in short. As I explained, right? This is assume this is your matrix describing user and items, right? This is if you have 1 million user and 1 million items. It's a very huge matrix, right? A million by a million. It's a trillion cells, right? Each one, if we call it a cell, you have a trillion cell. This is very hard to deal with, okay? So the key idea of matrix factorization is to come up with a sort of vectors, right? Describing a particular user and describing a particular item. And we capture those vectors for users in one much smaller matrix, and we capture the vectors describing those items in another matrix. If we multiply these two matrices together, then we come up with a user product rating matrix. Okay, the idea is that we want to optimize, we want to find those parameters right in those matrices, so that the prediction on existing items, right, on existing user item pairs are as accurate as possible. So essentially, this is an optimization problem, and the way we solve it is to perform gradient descent. Okay, and don't worry about implementing them by yourselves. We do that in parallel, and we take care of all the computation for you. Okay. So essentially, we derive a customer's signature vector and item signature vectors. And once we have the vectors, it's pretty easy to compute. Hey, based on your user's feature vector and a particular item's feature vector, we just do a dot product. We can easily come up with a rating for you. Now it's time to show a quick demo. So Jean, can you see this browser screen?
Yeah, looks good.
Okay. So this demo is to use a personalized PageRank PPR to build a recommender system. We have a movie graph. Okay. In this graph we have user and the movies. A set of there are two kinds of vertices, right? Users, movies. And
Z, sorry to interrupt. Could you actually increase the screen size on the demo? Great, thanks.
Okay, is this better?
Yeah, that's better. Thanks.
And then we model this as graph, right? Bipartite graph. Load them up into one of the backend. It doesn't matter. You can choose Apache HBase, even if it's Kerberos enabled, right? Or Oracle NoSQL database or Oracle relational database. You read that from the database into PGX, the in-memory analyst, and then with a single API call, you can run PPR and start the recommendation. Here we are using a Groovy shell. In this Groovy shell, you can just pretty much copy and paste the Java code snippet. Here we start with a graph configuration. The movie name, right? The graph name, use a movie, and we create a session. So this has already been covered in our BELS portion. We read the graph from the database into PGX. Let me pause a quick sec. This is the number of vertices, about 9,000 users and movies, and 300,000 edges. Okay, each edge records a click relationship between a user and a movie. So the edges, right, are very straightforward. If a user clicked on a movie, there's one edge. Okay. So now we have this graph. We started with creating a text index. Okay, why do we do that? Because we want to recommend movies for a user, right? But how do we find a user, right? So we rely on text index. So here we are we're building a Solar index. We have a very nice and tight integration with Solar Cloud. So with a very simple API call, you find a vertex, right, with first name containing a particular keyword. You can use wildcard search and all kinds of, using our Solar query syntax here. Okay, so here we're trying to find a guy with the name Nathan something. Okay, and we find one Nathan Nell. It's in Rotterdam. His age is 36, etc. There's different properties. So we're dealing with a property graph. So now our goal is to find, given Nathan Nell's existing clicks, right? Because he's a user in the graph. He has watched some movies, clicked on some movies before in the past. Right? Now, given that information, what new movies can we recommend? Okay. So we create a sort of a starting point, right? In this case, this starting point, this vertex set contains just this particular individual. And then we run PPR, personalized PageRank. This is really fast. This algorithm is implemented in parallel, right? Can leverage multi-core on modern computer architecture. So we take care of all those details, so you don't have to worry about it. Now, we want to get existing clicks, right? This individual has done in the past, because it's kind of silly to recommend the movies, Nathan Nell has watched before, right? Back to him. That's kind of silly, right? Isn't it? So we take care. We use the sort of the DAO API to say, hey, what existing edges are there from this individual? Okay, and then we iterate through the PPR result, and we try to filter those existing movies. Nathan Nell has already clicked, and then start showing the result. In this particular case, okay, we see there's a vertex, right, with a PPR value 0.008, and the plot is a time machine. The title I think is a time machine, and the whole plot of the movie is here. Okay, as you can see, this is a very easy process to build a recommender system. Okay, using the built-in algorithm PPR. All you have to do is to model your data in a bipartite fashion, and then given an individual, right, you build a vertex set, you run PPR, you iterate with the result, right? So those give you the highly ranked vertices, right, that are similar to your starting point. You can recommend those as either the movies or as similar users, right, to your starting point. So far, I have shown this using Groovy. In the interest of time, let me jump to the the Jupyter part. Okay, so you can also use Jupyter notebook to run the whole flow. Okay, Jupyter here you have to use Python, but through JPipe we can easily invoke Java APIs in Jupyter notebook. Let me pause a sec. Okay, so here we are invoking personalized PageRank against the in-memory graph, right? By providing Nathan L as the start vertex in this vertex set. Okay, and then you can iterate through the PPR result. Then you can even do a lot of charting with Python. There's so many plots you can build, right? So this bar chart shows the top 50 recommended vertices. Right? Some of them are actually users, others are movies. Okay, hopefully this gives you a quick idea how to use a personalized PageRank to build a recommender system. I also have a demo on using collaborative filtering. The idea is very similar. So you build a graph, right, in a particular way, and then you run a single API, and then you can, in this case, you use a model. Here we have, matrix, two matrices, right, behind the scenes, and that model can help you to come up with a rating, okay, between a user and a new item, okay. But I don't have time to get into this now, so let's move on. So the second use case is fraudulent behavior detection, and specifically we are interested in detecting a circular payment in the text in the finance area. Now the business requirement is to detect n hop, okay, circular payment. So imagine a loop with n hops, with n edges. So this kind of pattern shows up quite a bit in real-world transaction data. And in this particular use case, we are using some real data from a tax department in China. They want to catch this, fraudulent behavior, right? So say, imagine there are three users, right? A pays B, B pays to C, C somehow pays back to A. Okay, they're conducting this kind of fishy transactions to minimize paying tax. This is other original data, right? In graph format, the OPV and OPE format. So we describe this format in the first AskTOM. So if you're not familiar, just go back to the first video. As you can see, right, all those vertices IDs are long integers, right, and there's a lot of IDs like this because this is real data. So the username have been obfuscated with the long integers. Okay, the key information is here, right? Is on the edges. So this part, this box, shows a snippet of the vertices, and the bottom box shows a snippet of the edges. The key relationship is, a buyer bought something from a seller. Okay, so each edge encodes that purchase relationship. And we have a pipeline to detect circular payment. First one, of course, we have to model that transaction data into a graph format and load into Oracle property graph database. There are two approaches can be used to detect circular payment. The first one is to run PGQL to find the patterns, right, the circular patterns. The second one is more flexible, okay, to use one of the built-in analytics, strongly connected components, right? And then we can visualize the results. So PGQL is not the focus of this talk, but just to give you a rough idea, right? As you can see, right, the first PGQL query has a pattern. So we start from a particular individual M, okay? Going through one edge in this graph is a purchase, right? So M purchased from N, a different user, and then N purchased back from N. So it's sort of like it's a very simple, very tiny loop, right? If we want to detect a slightly bigger loop, so from M to N to O to M, back to M, okay? you can even create an even bigger query, right? And report back all those individuals that are participating in this specific behavior. You can add all different, right? To say, hey, I don't want to have duplicates, in this loop, right? Or if you want to reverse edge, you just instead of larger than, you put a less than here. Okay. I want to talk about strongly connected components, SCC. This is one of the built-in algorithms. If you think about it, right, if there's a loop in the graph, a loop means that it's a cycle, right? Then the cycle has to exist in SCC because every single vertex on this loop is reachable from any other vertex on the same loop, right? So they have to exist in the same SCC. So by doing strongly connected component, we can detect in one shot all those loops, no matter how big the loop is. Okay, so this is really powerful. The way to run that, again, is very simple. Here I'm using a Jupyter notebook. Okay. Let me show the demo. So here we are using a big data spatial and graph. The backend is Oracle NoSQL database. We're using Jupyter Notebook and JPipe. So this is the paragraph. We create a graph config. This is pretty much the same as that in Zeppelin or in Groovy. Okay. We load the graph into the database, NoSQL database, right? Just to give you an idea. So here I'm showing very simple graph. Okay. So that you see clearly how we detect the loops. There are 9 vertices, 1, 2, 3, 4, 5, all the way to 9, and there are a few edges, right? From 1 to 2, 2 to 3, and all the way to 5, and 5 back to 1. So that's a clear cycle, right, among the first 5 vertices. Let me speed up a little bit. Okay. So we finish loading up the data into the NoSQL backend, and then we issue a simple PGQL query so that you take a quick look at the vertices and edges, right? So those are the edges and the vertices, based on very simple PGQL result. So now let's get to the analytics, right? With a single API call, we compute SCC using Raju algorithm. There's another algorithm you can use. And there are 4 components, okay? If you iterate through the 4th component, right, the community, if you will, right, you will find there are 5 vertices in a particular community. Okay, those 5, if you plot them out, right, you will see they form a nice loop. Okay, so this is really powerful because you don't have to tell the query, hey, I want to find out 6-hop loop, or I want to find out 3-hop loop, right? It's able to find the k hops, right, in one shot. Now back to the slide. Not this one. So we run, SCC, right, on the real world data, and we visualize on the screen, right? So those are purchase relationships among individuals, right? From a buyer purchase something from a seller, right? By using the SCC algorithm, we can easily pinpoint all those circular payment behavior. Okay, whether it's 5 hops or 3 hops here. So the visualization here is done using Cytoscape. We're going to talk about the visualization in our next session. So this, hopefully gives you a good idea how to use a built-in algorithms, built-in analytics to find and detect a fraudulent behavior. So now back to you, Jean.
Great. Thanks a lot, Z. Great use case examples there. So we are just about 5 minutes from the end of our hour here, so I will share with you some resources for your future reference, and do feel free to enter any questions you may have from Albert and Z's material into the chat. We'll probably have time to address a couple of those questions as well. So we have a vast number of resources available on our product pages, the first two URLs you see there, both for the spatial and graph and the big data spatial and graph products, including collateral papers, software downloads, videos, and documentation. We have two blogs that Z is great about keeping up to date with the latest tips and tricks on using both the big data and the Oracle Spatial and Graph products there. So check those out as well for some helpful tips and tricks. We have a YouTube channel as well with a number of videos ranging from intro videos, business use cases, customer cases, as well as technical tutorials, including the AskTOM series and many more at the URLs that you see. And we've highlighted one from a partner that's a particularly good one for newbies getting started on the database platform. And finally, we've taken a look at some examples from Z and from Albert on big data platforms today. There is a downloadable virtual machine that you can get for free if you'd like to get your feet wet in using these technologies. It includes both the big data spatial and graph product, the database, as well in that VM, and a hands-on lab includes a couple of similar examples to what Z has shared with you today. Next slide. Z, if you could, great, perfect. To deep dive a little bit more into the graph analysis algorithms that Albert and Z have discussed today, here's the documentation pointer that is a great resource to read more about these specific algorithms and what their capabilities are. Next slide. And finally, we're available both on social media channels as well as through user groups. Feel free to follow us on Twitter and to find our user groups on LinkedIn and Google+ to interact both with us as well as other customers and partners in the community, and to learn about the latest events that are going on in your geography and online. Next slide. And again, here is the AskTOM landing page for our property graph sessions. Come to this URL to view past recordings and get the recording from today's session. Our next session will be on July 17th, and we'll dive further into graph visualization with Cytoscape and perhaps with some other tools as well. And I just wanted to remind you, you can also give us feedback and submit follow-up questions at that landing page. We'd love to hear your feedback. If you do submit a question there, do include an email address or a way that we can connect back with you. You can also set up a profile at that website. So any questions from the audience? I know it's a lot of great material that Z and Albert have thrown at you, so I guess everybody's digesting. Here's one question from Arthur. Any plans for Docker images? Z, do you have any insight on that one?
Yeah, so Oracle Database 12.2, there is a Docker image out there. Once you pull that into your container, spin it up, it's very easy to run a few configuration steps to enable 32K biochar, and then you can use that as a database, right, as property graph database, and store the data, right, run all kinds of stuff. So that is available also. Will that be useful to you?
I think Arthur's muted, but Arthur, feel free to drop a line in the chat or give us a buzz after the session if you like. Oh, okay, looks like he replied. Yes, and he's also wondering about Zeppelin integration, Z?
Yeah, the Zeppelin integration is there in 12.2. there's also a patch, right? We have a patch ID. Just to drop us an email, and then I can point you to the patch. So you can grab the Docker image for Oracle 12.2 database, and then install the patch so that your property graph functions are up to date with the latest Zeppelin integration.
Okay, awesome. Yeah, thanks, C. So it looks like we're at the end of our hour. Thanks, everybody. And we look forward to seeing you in July for graph visualization. Have a great day or evening, everybody, and we'll close out the session.